Hi, welcome back. Let's talk about another type of calculus that we can do on polar curves. So we have some function that's defined r as a function of theta. And what we'd like to do is we'd like to figure out what's the arc length of this curve. So how long is the path that this curve sweeps out? So in this setup, we're still going to be using the idea that arc length is equal to the integral of little bits of arc length. So we're going to zoom in here on one small bit of this arc length. So this curve is moving. I mean, is changing radius. So um, if we zoom in here, what do we see? We see that we're just some distance r from the origin, and we have swept out a small amount in here of d theta. And so the question is, how long is this segment that we've swept out? And so to do that, what we'll do is we'll use again um, the Pythagorean theorem, and we'll say, okay, how big, if we're looking for dl, how much is there on each side of dl? So if we look at this, how much has uh, the, the radius changed? Well, there's some little dr that the radius has changed. And d theta is not the same as this distance that's on here. D theta is the angle that's swept out. So for instance, if you think about it, if this is the angle theta, d theta, then for different distances from the origin, this length is going to be bigger, right? So if your distance r away from the origin, then if you swept out an angle d theta, then this distance is r d theta. So what that means is that in our Pythagorean triangle, then the sides of the triangle are dr for the distance away from the origin, and rdr for the the horizontal distance. So what we get is that this integral is going to be the integral of the square root of rdr. Oops, sorry, not rdr, rd theta. Rd theta plus that squared plus dr squared. And so remember, this is a function of theta, so we need to now put everything in terms of theta. So what do we get? We get the integral of square root of r d theta squared plus d theta, oops, dr d theta squared. And so we get our formula, the integral of square root of r squared plus dr d theta squared d theta, where our integral goes from the place where we start chopping to where we stop chopping. So theta equals alpha to theta equals beta. And so we get this equation for the arc length of a polar curve. Now, what I like about this presentation is it really just starts from the idea that arc length is the integral of a whole bunch of little bits of arc length. And but if you'd like, there's another way that we could see this, and that is that we can because we now could see polar curves as parametric curves, we could apply the function for parametric curves. So another way to calculate this is to say, okay, we already know that the arc length is equal to the integral from theta equals alpha to theta equals beta of the square root of uh, x primed of t squared plus y primed of t, or theta, squared d theta. This is our arc length formula uh, from parametric functions. So what that means is we have the theta equals alpha, theta equals beta, square root, and now we have to take the derivative of r cosine of theta, and then the derivative that, then square that, and then do r sine of theta, take the derivative of that and square it. So what's the derivative of r cosine theta? Well, it's the first times the derivative of the second times negative sine theta plus the derivative of the first times the second squared plus r first times the derivative of the second cosine plus dr d theta times sine of theta squared. All right, this doesn't look too beautiful. Let me give us a little bit more space here, and I'll bring these things down. What do we have here? We have uh, negative r sine of theta plus dr d theta cosine of theta squared plus r cosine of theta plus dr d theta sine theta squared. So as we expand, what do we get? We get r squared sine squared theta minus r dr d theta sine theta cosine theta plus dr d theta squared cosine squared theta. That's the first piece. And the second piece gives us r squared cosine squared theta plus, oops, I should have put a 2 here, sorry, 2r dr d theta sine theta cosine theta plus dr squared d theta times sine squared theta. All right, so this term, oops, this term and this term cancel out, they add to 0. And what are we left with? We're left with r squared times sine squared theta plus cosine squared theta plus dr d theta squared times cosine squared theta plus sine squared theta. And that's making us feel much more comfortable because we have a nice identity. These are both equal to 1. And so what that means is taking this, putting it back in, what do we get? We get this is equal to the integral from theta is equal to alpha, theta equal to beta of square root of r squared plus dr d theta squared d theta. All right, so we can see in both of these ways, we can calculate what we get the same answer for what the arc length is of a polar curve. All right, so let's stop there for now. We'll do some more calculus on polar equations shortly. See you soon.